Wonderful. Well, thank you so much for inviting me. And yeah, it's a pleasure to be giving this lecture for this Terahertz series. So basically, today I'm going to be discussing kind of a few topics relating to quantum cascade lasers, and I think and specifically broadband frequency combs as well, and also comb applications. I believe, and hopefully I'm not mistaken, I'm probably the only person discussing quantum cascade lasers, so I'm going to be giving a little bit of an overview of that area as well, at a very, very high level picture, and then we'll move on to our discussion of combs and comb applications. So what is the terahertz range? Well, I think you've probably heard a little bit about this already from the previous talks, but basically it's the range that falls between the microwave and the near infrared and far infrared, or near and mid infrared range. And it's a range that's useful for non-invasive inspection, bio applications, communications, and especially for kind of our purposes today, spectroscopy, especially given that many molecules have unique features in the terahertz range. So why be interested in long wavelengths or terahertz more specifically? It's mostly, or at least in my opinion, especially within the 1 to 5 terahertz range, which is going to be my emphasis today, it's primarily spectroscopy. So of course, many large gas molecules and also solid and liquid molecules have distinct spectral lines in the terahertz due to combinations of rotational and vibrational transitions. There's this pretty famous plot from TeraView from a few years ago demonstrating unique absorption signatures of various explosives. And in general, the terahertz range is nice because this is where, in contrast to the mid-infrared, which has features corresponding to many smaller molecules, the terahertz often has much larger ones. And so, of course, there's also this famous demonstration of terahertz drug detection, where basically what you can do is you can shine broadband terahertz radiation onto these various powders and determine through some analysis that what each component is actually being comprised of. So you can detect, for example, aspirin differently from an illicit drug. So of course, this is measured in a lab and under close to ideal conditions. And from my perspective, as more of a device on the device side of things, what we're interested in doing is making sources and systems which can actually improve the possibility of these sorts of applications. So there is this very classic notion that comes up again and again in terahertz, the terahertz area, which is this notion of a terahertz gap. So basically, let me add a pen here, a pointer. So the challenge for the terahertz range has always been that if you try to use traditional electronic techniques, such as relying on transistors, then the power rolls off very quickly as you approach very high frequencies, just due to the transit time, essentially. And in terms of photonic techniques, what you run into is challenges of selective injection, and especially for interband diode lasers, what you run into is the band gap of the material. But terahertz quantum cascade lasers actually do quite a good job at filling in this range, especially between the 1 to 6 terahertz range. Although there's still a little bit of a gap that is still quite unfilled in the 6 to 11 terahertz range, I would say. And so today's talk is mostly going to be focused on this technology, which is of course nice because it's a semiconductor technology, and so you can make everything here relatively chip scale. And then later on for this, I'll be talking about broadband frequency combs as well, also applications for these things. So here's the outline for today's lecture. The first part of my talk is really going to be kind of a very broad overview of terahertz quantum cascade lasers. So this is something that, well, if you're an expert in the area, then you've probably seen many of these things before. But otherwise, I'll try to keep things at a very like big picture view. Of course, I'll be skipping over a lot of material, and actually, a lot of the material I'll be discussing is in this area is quite several years old at this point. And then for the second part of the talk, I'll be discussing broadband frequency comb formation in terahertz quantum cascade lasers, which is useful for spectroscopy. And then in the last portion of the talk, I'll be discussing some new applications for combs in terms of spectroscopy and also radiometry. So, so what is a terahertz quantum cascade laser, or what is a quantum cascade laser in general is the first question we need to answer. So if you've done any photonics, or even if you haven't done photonics, you've probably encountered semiconductor lasers at some point. And a semiconductor laser is one of the major successes of semiconductors generally. And probably the workhorse of this area are interband diode lasers. And a diode laser is a relatively simple electronic device, but a more complex photonic device. It works by essentially using a p-n junction. And of course, you can modify it by adding quantum wells and add lots of bespoke features to a diode laser. But ultimately, it's all relying on interband transitions. So basically, what you're doing is you are getting a population inversion. So in any laser, you need to have electrons living in an excited state relative to a lower energy state. And in the case of a diode laser, it's by injecting electrons and holes into the same material. And so if you have electrons and holes in the same place, then really what's going to happen is you have a population inversion, and you can get gain between these two sets of states. But the challenge with this is that every semiconductor has this quantity, which is known as the band gap, which determines basically the lowest energy that you could ever hope to achieve lasing with. And this is essentially a property of the material. So so if you wanted to make something that's lasing in the terahertz or even in the mid-infrared, that's very challenging just using a conventional semiconductor material. Now there are actually low band gap materials, like for example Mercatel, but actually there's a secondary issue when it comes to low band gap materials, which is that it's very difficult to actually select to achieve selective injection. So in low band gap materials, in other words, it's very hard to actually achieve any population inversion at all. And so this seems like it should be a showstopper for frequencies that are below the band gap of most semiconductors, which tends to be about the the mid-infrared is where this becomes a dicey prospect. And so that for a long time, of course, this was the case. There were no semiconductor lasers in the mid-infrared or terahertz. And then that was until the first quantum cascade lasers were made. So these were made, first demonstrated anyway, in 1994. They were actually first theoretically proposed in 1972 by Kazarinoff and Suris. And essentially the idea is to use quantum wells where you are relying on the inter-subband transitions of the states inside a quantum well to achieve lasing. And this is actually a very different phenomenon than interband lasing. So actually, each of these states in a quantum well is well, in one direction, it's a wave function, and then in the direction that's perpendicular to this, so-called lateral direction, the electron acts as a plane wave. So it's free in 2 dimensions, but it's bound in the last dimension. And it turns out that because the bands are all curving in more or less the same way for each of these subbands, you can actually achieve first of all, you can achieve very selective injection into an individual state by relying on tunneling. But secondly, you can actually achieve gain between different pairs of states. And importantly, because you can design the energies of these states and also their shapes based on the shape of the quantum well, then you can actually really have a lot of design flexibility in making a laser that lases in the mid-infrared and terahertz. And so this was first demonstrated in the mid-infrared in 1994 at Bell Labs by a team including Jerome-Based and Federico Capasso. And this has kind of become, I would say, the most, in many ways, it's one of the most successful platforms. I guess I would argue that in the sense that it is probably the only laser system that can cover, well, maybe it's okay. So it's not as broadband as a free electron laser, but it can cover at least 2 orders of magnitude in terms of frequency. Free electron lasers can cover a bigger range, but they're very, very large systems, whereas these are semiconductor lasers, so they can actually be essentially microscopic, or at least microscopic in most dimensions, except for one. So quantum cascade lasers have been around for actually this is the 30-year anniversary, so they've been around for quite some time. And so why are they called quantum cascade lasers? They also have this feature that because they're relying on quantum wells, you can actually lase multiple times inside the band diagram, or sorry, inside the structure. And there's this cartoon picture that Jerome Feist made quite a while ago, and basically the electrons can transit through the structure, emitting multiple photons, and so actually you can emit essentially n photons per electron. So your quantum efficiency can actually be much greater than 1 in certain cases. And actually you can really, your quantum, just because your quantum efficiency is high doesn't mean your actual efficiency is high, but it's, what's nice about this is that you can actually have a large interaction of your electron with the field. And so you can see that when the electrons are emitting photons, they're very happy, and when they're in these regions in between, they're a little bit less happy. And this region here is in between is called the injector, basically where you're kind of collecting electrons and preparing them for injection into the upper state. And then once they're in the upper state, they emit a photon and they go into the lower state. So that's the general idea of a quantum cascade laser. Well, what about terahertz quantum cascade lasers? Terahertz lecture series. Well, they were actually, quantum cascade lasers were originally proposed as being ideal for terahertz. And in fact, I wasn't around at the time, but my understanding is that at Bell Labs and in several other groups at the time, there was a few groups trying to demonstrate terahertz quantum cascade lasers. But actually, it turned out that terahertz quantum cascade lasers are much more challenging than mid-infrared ones. So I believe, like for example, Jerome Weiss had been working on terahertz quantum cascade lasers, and then eventually decided to try making a mid-infrared one because he thought it would be quite a bit easier, and that was correct. And basically, the reason for that is that you can maintain population inversion in the mid-infrared for mid-infrared transition, where the energy is quite large, much more easily than you can in the terahertz range. And there's a couple reasons for that. One is that the energy levels for terahertz, where the energy is even smaller, is of course much smaller, and so you need to have much more selective injection. So in other words, when you have electrons going into the system, you can't have electrons leaking through to other states. You only can inject into this state. But also, the other issue you run into, and this is especially the case at higher temperatures, is that there are a lot of scattering processes which will deplete the population of the upper state when the energy levels are spaced together, which is less the case than in the mid-infrared. Now, this actually cuts both ways. This can be used for example, in this design that I've shown here, where you can actually depopulate the lower state of the laser, and this is helpful for maintaining inversion. But I'll get into that in a second. So terahertz quantum cascade lasers were demonstrated quite a bit later in 2002, so still quite a while ago, 20 years ago. And that was done using this so-called chirp superlattice design, which is basically, if you look at actual quantum cascade laser designs, this is very jargony sort of, but what this is showing a collection of wave functions and also what the energies are of these wave functions. And so in this design, the states that are lasing are state 3, and state 3 is the upper state. State 2 is the upper state. State 1 is the lower state. And then you basically can sort of imagine that once an electron is in this lower state, it can couple to all these other wave functions and just kind of tunnel over into the next upper state. So every electron is essentially going from its lower state and then kind of transiting into its other one. Now this design actually is not so commonly used anymore, but it was very useful for achieving lasing in the first place, and they achieved very definitive lasing that you could see just by turning the laser on. So as you turn the laser on, at first at low currents, you see just electroluminescence. That's these broadband plots here. And then as you go up in current, the electroluminescence narrows, and then you get this very sharp lasing transition in the spectrum. And this is at 4 terahertz. By the way, I believe the current record operating range for a terahertz quantum cascade laser is between 0.8 terahertz and 6 terahertz. So nothing is ever lased outside that range. So this is the first design. So kind of how did this work? So this is the gain medium, but for a laser, you actually have 2 aspects that you need. You don't just need a gain medium, you also need a cavity that can store the light. And the terahertz range, you run into other challenges in that regard. So you need a very low loss waveguide that's not going to kind of throw away your light. And kind of the first waveguide design that was implemented is semi-insulating surface plasmon waveguide. So this is a waveguide geometry where basically you have a metal layer on the top and then a very highly doped layer underneath your gain medium. So this striped region in between is actually where you have your quantum belts. And well, you can actually show that the lasing mode is mostly confined between the metal layer and this highly doped region. Basically, the highly doped region you can think of as kind of reflecting the light somewhat, so it keeps the light on the inside of this thing. Or you can think of this as a plasmon waveguide. But this design, it's nice in that it has a very nice beam pattern, generally speaking. It has one downside, which is that a lot of the lasing mode actually goes into the substrate. So the substrate, in other words, this bottom portion here, a lot of the light actually lives inside this, and that's because the wavelength is so long that it wants to go down into the substrate. So later on, these metal or so-called double metal waveguides were introduced, and these waveguides are actually very much like microwave microstrip lines. So you basically sandwich your gain medium between two strips of metal, and this is a little harder to fabricate because it involves wafer bonding. That's the only way you can get the quantum wells to be sandwiched between these two strips of metal. Of course, you can't actually grow quantum wells on top of gold, but actually, it turns out to be a very nice waveguide for most terahertz QCLs. This is actually, I would say this is a more versatile waveguide for most terahertz QCL applications. What's nice about it is that because your mode is completely within the gain medium, for all intents and purposes, the overlap is very high, and so in other words, all of the light actually sees the gain medium, and so you get actually very good temperature performance, or the best temperature performance out of these sorts of designs. The one downside is that the beam pattern is usually worse, and also it's actually hard to extract light out of this structure sometimes. So most QCL designs these days, I would say, tend to fall into this category, the metal category. So, like for example, in my group, we mostly don't even actually make SISP waveguide-based designs. And in terms of the gain media, there's kind of two types of gain media that are really dominant. Of course, there's many different designs, hundreds, maybe even thousands of designs that have been made over the years. In other words, different quantum well designs. Each of these periods, by the way, is called a module. And kind of the two that are most dominant are the so-called bounded continuum design, where you have a single state coupled to a collection of continuum states, actually a little bit like the Chirpster lattice design. And these bounded continuum designs, they tend to be very vertical, which also means they have high gain and low thresholds. But they also usually have worse temperature performance than the other design that I'll talk about, which is the resonant phonon design. The resonant phonon design is a little bit different. So in the resonant phonon design, you actually have just one state coupled to your lower laser level, which is the purple curve here. So you extract electrons. So after your electron emits from the red state to the purple state, it tunnels into the pink state, and then it seems like it has nowhere to go because like if you just look at this compared to this diagram, for example, all the wave functions are kind of like overlapping each other in energy. Here, there's nothing else here. But it turns out that actually, if you separate this from the next state by the energy of a phonon, which for gallium arsenide is about 36 MeV. So this is the energy of an LO phonon, which is basically where is the main optically active phonon in 3-5 materials. Then you can actually depopulate this lower state very efficiently and achieve population inversion. So these structures tend to have higher thresholds, but also better temperature performance. So one of the major challenges for terahertz quantum cascade lasers for a long time, and it's still the case, is their temperature limitations. So it turns out that because we are essentially dealing with energies that are usually much lower than K times T. So at room temperature, K times T is 25 MeV. So for 3 terahertz, you're dealing with something on the order of 14 MeV. We're dealing with energies that are actually lower than that. So you might worry like, oh, is it impossible to achieve inversion? Well, it's not impossible, but it becomes progressively more challenging. And actually, at elevated temperatures, what happens is this LO phonon energy separation actually becomes a major limiting factor. And the reason for that is that electrons that are living in this upper state, these are actually not individual states, these are subbands. And there are electrons at room temperature, for example, which are living up here. And these electrons can also emit phonons down to the ground, to the lower energy state, because this energy separation can be the LO phonon energy separation. Right. So if your frequency is 16 MeV and your LO phonon energy is 36 MeV, then roughly speaking, you only need this to be about 20 MeV, which of course, if room temperature KT is 25 MeV, then you've already satisfied at room temperature. And so the temperature performance of these has never actually achieved room temperature. There's been a lot of progress over the years. So you can see there was a lot of fast progress very initially. So it very quickly reached into the 150-ish, 100, almost 200 range. And then it kind of really plateaued off for a while, although there's been some recent work which actually kind of really pushed this into the regime above 200 Kelvin, where you actually can operate these things using thermoelectric coolers. So below 200 Kelvin, you basically need cryogenics for the most part, but between 200 and 273, you can use TECs, which are not so bad. So especially in the last couple of years with these 250, 261K results, the temperature performance has gotten quite a bit better. And so there is hope for room temperature operation, but it's still very challenging. And also this is specifically at 4 terahertz. So if you I didn't show this plot, but if you try to go off center from 4 terahertz, your temperature performance is also going to be falling. So 4 terahertz turns out to be about the sweet spot for terahertz quantum cascade lasers. It's a combination of, it's basically the highest frequency that you could achieve without actually seeing an absorption band from the yellow phonons. So kind of these recent designs, these high barrier, high temperature terahertz these high temperature designs, these are all high barrier designs. So the earlier designs all relied on low aluminum fractions. So in other words, the barriers had aluminum fractions of about 15%. And these recent designs have had much higher barriers on the order of 30 to 35%. They take much more power actually as well. But the trade-off is that their performance is better at elevated temperature. So this is an exciting area. I think for a long time, personally, I didn't think that even this is, by the way, this is all in the same material system. This is all in gallium arsenide outgas. Of course, there's always interest in new material systems. The 3 nitrides, for example, antimonides, and then more exotic materials as well, topological materials and so on and so forth. But I should emphasize that for quantum cascade lasers, one of the major innovations that was needed is ultimately high quality material growth. Quantum cascade laser growth is amongst the hardest. I'm not a material growth person, but I'm told it's amongst the hardest structures to grow, just in terms of the level of control and interface roughness, and also calibration needed to grow these large structures is very resource consuming. So of course there's a lot of nice applications that you can do with single frequency quantum cascade lasers, and I'm not going to go into all of them. And a lot of very compelling work in other types of devices that have been developed over the years. I kind of want to talk a little bit about astronomy. So one of the really compelling applications for Terahertz quantum cascade lasers is in astronomy. So there's been several missions and also planned potential missions that are actually using Terahertz QCLs for measuring various interesting features. So GUSTO is for measuring interstellar oxygen. Actually, I believe the great spectrometer was as well. So GUSTO is an upper atmospheric balloon. The great spectrometer was on SOFIA, which is an upper atmosphere plane which has an observatory on it. So it's an observatory on a plane that stayed in the air for I think years, but that mission ended, and there's been some discussion of actually putting a terahertz quantum cascade laser on the moon as part of the new NASA Artemis missions. And that's because the terahertz range is very good at measuring water concentrations, for better and for worse. If you've done terahertz, you know what I'm talking about. Turns out that water is very absorptive in the terahertz range, especially certain terahertz frequencies, which is great if you're trying to detect water on the moon. Not so great if you're trying to do measurements over a long path length, because water is everywhere on Earth. But yeah, I don't know if this has been greenlit yet, but there is some progress towards this. So that's kind of the general view of terahertz QCLs. Next, I want to kind of move on to this work on broadband comb formation in terahertz QCLs. So I mentioned earlier that spectroscopy is something that is very compelling for us, especially in the 1 to 6 terahertz range, where I think communication is very much a hard sell. Communication, of course, requires transmission over a large distance, and you can pick a transmission window, but nothing. The atmosphere is just not that transparent in that frequency range. But spectroscopy, there are a lot of good reasons for doing spectroscopy in this range. But to do spectroscopy, of course, that means you need a broadband source. And also, on top of that, you need some sort of frequency discriminator. So you need either a grating or a Fourier transform spectrometer. I believe Professor Sterczewski mentioned that last week and discussed that in depth. And wouldn't it be nice if there was something that could actually give you all of these things all at once? Not just the broadband source, but also a way to do spectroscopy and to discriminate between different frequencies. And it turns out that frequency combs are actually one nice way of doing this. So if you go back to this plot that I showed earlier, I mean, if you actually look at the power levels that are involved, some of these are actually quite high right there. They're a watt essentially, and so a watt is quite a lot of energy. And so you can imagine, are there nonlinear optical effects that happen? And the answer is yes. And one of the most compelling effects that has been observed for a while now is the formation of frequency combs. So a frequency comb, if you haven't heard of this before, it's a light source whose lines are perfectly spaced, or in other words, mode locked. So a comb is a light source where the lines are completely evenly spaced across the spectrum by this frequency that we call FREP, or the repetition rate. And it's called a comb because it looks like a comb, right? So this looks like a comb. And it turns out that this is actually nice because we can actually do very interesting spectroscopies with it. And also it's a broadband source. So let's not forget about that. So a broadband source is also useful in and of itself. The comb structure, having this actual uniform spacing, is also very beneficial. And that's because combs can enable simpler measurements. And really, it's the structure of combs that can enable new spectroscopies and measurement techniques. So if you have two combs, you can do what's called a dual comb technique. So if you take two combs and you beat them together, so if you take two light sources and you beat them together, you always get the difference of every light source that's involved. And if your two combs are slightly different, then what happens is, as you beat them together, different pairs of lines will beat at different frequencies. And the result of that is that actually what you record is actually this beat frequency is at a much lower frequency. So these frequencies are all at optical frequencies, but the beat frequency would be at RF frequencies. And so what you do is you basically encode your spectral information at optical frequencies into the electrical domain. And so this is really nice because you can actually do interesting spectroscopies with this. And QCLs are potentially a great platform for combs. They because you can have these different gain media in a single stack, you can actually make the gain media very, very broadband. And so if you mix different stacks together at different frequencies, then you can make these very broadband gain media, and then also these very broadband lasers, and maybe also octave spanning combs. So actually an octave spanning gain medium has been demonstrated. And octave just means that you contain a frequency and also double its frequency. No octave spanning comb hasn't been developed using QCLs. I'll kind of talk about why I think that is. But actually, it turns out that, how do you make a comb out of a QCL? It's been known for a while that they make combs somewhat naturally. This was really conclusively shown by Jerome Feist in the mid-infrared a little over 10 years ago. Excuse me. And it turns out that if you have a certain kind of comb, you can show that you actually, or a certain kind of gain medium, you can actually go into this very nicely uniformly spaced regime. And I won't go too much into the details of the nonlinear optics here, but basically it's because all of these combs really balance between the dispersion, which is the non-uniform spacing between different modes, and an optical nonlinearity, and then also gain and loss. And so one thing you can do in order to form combs, and this is what we showed in the Terahertz a little bit afterwards, so this was in 2014, we showed that actually by engineering the dispersion of these Terahertz QCL cavities, you can form relatively broadband combs covering the Terahertz range. And so one of the ways of doing this is using these double sharp mirrors. And so basically the idea is to design this structure which has a Bragg reflector that varies with position, and you can actually cause different frequencies to reflect at different positions inside this Bragg reflector. And so this actually engineers the dispersion of the cavity. And a lot of different dispersion engineering techniques have been developed over the years for quantum cascade lasers. And so this is something that you can kind of the main trick that you can play in order to engineer these cavities. It'd be really wonderful if you could make an octave spanning comb. This actually turns out to be the octave spanning point would be a very critical threshold actually for achieving broadband combs. They're not that close to octave spanning, to be honest, even today. But actually, there's probably more hope for this than there are for many other gain media. So there are very few gain media, or very few platforms that have octave spanning gain or close to octave spanning gain, just in general. And so then the question is, how can you make broader bandwidth combs? And there's been a number of different techniques that have been developed over the years, involving both Fabry-Perot cavities, which is more or less a linear cavity, and also ring cavities. I'm not going to talk about all of them. Some things I'll highlight is there was some recent work on passive mode locking in Fabry-Perot cavities. Also, this recent work on field concentration inside these cavities, where you concentrate the field and do a very narrow region in order to enhance the effective gain saturation. Rings are nice in that they have interesting soliton-like solutions as well. But of course, to really engineer this and to figure out what's happening here, you actually have to kind of understand a little bit about the nonlinear optics that goes into making these combs. And so kind of what I want to introduce is like a speculative notion is there a way to making this perfect QCL comb? So if you had a gain medium which has a bandwidth that's above threshold, so any laser has a threshold which is determined by its losses, and it also has some gain spectrum, and you would ideally like to be able to laser over this entire range where your gain is greater than your losses. And so this would be kind of the ideal situation. Of course, you also like these lines to be nice and uniform in order to actually have a comb. And for years now, there's been kind of well-established techniques for making combs, and they can kind of fall into one of these two categories. One is the first one that was developed is active mode locking. So what you do is you you modulate inside a laser, you modulate the loss with synchronously with the repetition rate. A little bit later, people developed passive mode locking. So passive mode locking is this technique where you modulate, get a pulse to modulate itself. So both of these techniques are fall in the category of amplitude modulation. So if you modulate the loss inside of a laser, you'll generate these pulses inside the cavity. And so these pulses in the time domain actually generate cones in the frequency domain. A periodic pulse train, if you Fourier transform that, gives you an array of cone lines. There's an alternative way, just known as Fourier domain mode locking, where you modulate the phase of a field inside a cavity. This is actually producing a constant intensity, but a chirped frequency. So actually, it's kind of the opposite of a pulse. The intensity is more or less fixed, and the frequency is changing. So this is very much like a frequency modulated sort of source. But unfortunately, it's been known for a long time that QCLs are very difficult to mode lock. They have a short T1. And also, FDML is somewhat limited on chip. So then the question is, like, what are these comb states that people observe in QCLs? And it turns out that while they're relatively easy to make and have actually been observed in some sense for 25 years, the understanding has come much more slowly. And there's been a lot of reasons why, but what it comes down to is, I would say, a few things. One is kind of randomness and MBE. Second way is that it was difficult to measure the profile of these structures. And then lastly, the simulation kind of becomes very challenging. So there's a lot of parameters that can go into a simulation. It becomes very hard to pick an answer for why a given effect is occurring. So unfortunately, while quantum cascade lasers are kind of one of the triumphs of material beam epitaxy, it turns out also that even nominally identical growths in MBE in the same reactor can sometimes produce wildly different results. So you get these effects like frequency-dependent gain, which are very dependent on the growth run. So in other words, almost every wafer that you get with a quantum cascade laser is a little bit unique. So they're not all exactly the same. And so while you can get many lasers out of a single wafer, achieving a really perfect uniformity between wafers is actually quite a bit more challenging. And so also there's effects like bias dependence of the gain and the group velocity dispersion. Even just measuring the gain and losses of quantum cascade lasers can be very challenging for reasons I won't get into. But probably the big factor that I think held this area back for a long time is kind of really just the understanding of even what was happening when these combs form. So even going back to 2000 at Bell Labs, there are these results showing that you could get these very broadband spectra with very narrow beat nodes. I'll explain what that means in a second. So basically, if you have something that looks comb-like, but maybe it's a comb, maybe it's not a comb, you don't know to start with. One way of checking to see if it's a comb is to just take all the lines and shine them on a detector. And what you detect is the beat frequency between all these lines. And if the beat frequency is narrow, and there's just one beat frequency, then that's usually a pretty good indication that actually you do have a comb forming. But unfortunately, this is really not enough for metrology purposes. And also, this tells you no information about the phases of the lines. So actually, the phases of the lines are what you need to know in order to figure out actually what the profile of these combs were. And actually, I say this is a QCL thing, but it's actually not even just a QCL thing. This is actually a semiconductor laser thing more broadly. So it turns out that if you go back to, for example, some early results from Reeves' group in the 80s, they were seeing these same sorts of narrow beat nodes in broadband spectra, where people would call it mode blocking, but they wouldn't necessarily do that much analysis, and there wasn't a lot of analysis that you could do on top of this to figure out actually what is the profile of these structures. And by the way, what do these frog and spider cartoons have anything to do with this? Well, frog and spider are very well-established, well-known techniques for measuring the shape of a waveform. Frog and spider are acronyms. So, and it's there's a classic result from Ian Walmsley, who used to, well, he's not anymore, but he used to be the head of Optica, actually, or the OSA. And they showed actually that you need nonlinear optics in order to do phase retrieval. To actually figure out what the phases are, if you have a slow detector, then you need to be able to do nonlinear optics on this to figure out what these waveforms were. And it turns out that actually these waveforms were not, at the time, people didn't necessarily know this, but they were actually not pulses for the most part. And so if you don't have pulses and you don't have high intensities and you're operating in the terahertz or you're operating in the mid-infrared, then it's very hard to do nonlinear optics generally. And so this kind of really held the area back. And so kind of the, well, not to toot my own horn too much, but there was a technique that I developed while kind of demonstrating the first combs, which is called SWIFTs, which is kind of the first, I would say, practical method for using linear optics to do phase retrieval, or maybe not practical, but easy. Easy is what it is. It's an easy method for using linear optics to do phase retrieval, and so that's so it's a technique that is basically only requires that you have a Fourier transform spectrometer as in terms of your optics. So the actual thing that was novel about it was essentially that instead of recording the regular power spectrum, what you're recording is you're recording the beat note, and you're actually more specifically you're demodulating the beat note at the repetition rate. So you're not recording. So you're recording the amplitude and phase of the beat note as a function of interferometer delay. And you can actually show that when you do this, what you measure is the difference between the phase of adjacent comb lines. And this difference can be shown to actually, you can actually reconstruct the phase using that, at least up to a point. So it's not a perfect measurement. There's still, of course, issues of signal to noise ratio and so on and so forth, but it's a measurement that you can use to recover the phase of these fields without using nonlinear optics. So the loophole, by the way, that gets around this Walmsley result is that this result is only for a slow detector. Actually, if you're using a relatively fast detector, a detector that can detect the beat note, then actually you do maintain some phase information, which was actually also shown in the Walmsley paper. But sometimes people forget about that part. So anyway, SWIFTs is a technique that's kind of grown in popularity a little bit in the last few years. So it's because it's a technique actually that can work at many different frequency ranges, really from the terahertz all the way to the visible, actually. So it's a technique that I would say is a little bit interesting in that it's one that started in the terahertz range and then moved on into these other frequency ranges. And it's SWIFTs doesn't really matter what it stands for. The most important thing is that a swift is a bird. So this, of course, has an animal name. Although more specifically, SWIFTs is actually plural, so you need to have multiple SWIFTs involved. So, of course, this satisfies the requisite name. But actually, it turns out that when you do this for all these different lasers, what do you actually get? Well, you get a regime that is much more like a frequency modulated or an FDML type laser than an amplitude modulated laser. And so again, we showed this first in the terahertz, but it turns out that the most common regime is actually a linearly chirped regime. And this linearly chirped regime is very interesting because it actually is quite nice in that the frequency is really just kind of sweeping linearly and then periodically repeating itself. And so kind of the cartoon model of this is that you have this constant intensity and nice linearly chirped frequency. So if you look at the actual electric field, the electric field looks like this. So it looks very different from a pulse. It's a periodically repeating waveform. And this linearly chirped regime was also quite interesting. You can kind of, this gets into the last issue that kind of impeded the understanding, which is the theory of this stuff. All lasers are governed by the coupling between Maxwell's equations and the Bloch equations, which are called the Maxwell-Bloch equations. But these are these are very nonlinear equations. I won't even write them down because there's really no point in a presentation like this, or really any presentation. They're long and they're nonlinear and they're all coupled together. So it's very hard to make analytical progress on them. And there's many different potential solutions. And of course, when you have a quantum cascade laser, there's many parameters that can go into describing the model. And so kind of a few years ago, and this was mostly like a pandemic project, you know, what I was interested in doing was kind of taking this formalism called the Lugiato-Lefebvre equation and applying it to these lasers. And when you do that, actually, you can do that to describe QCLs or really any semiconductor laser using this LLE type formalism. And importantly, this is able to replicate the FM portion with just essentially one equation that you can integrate very efficiently and accurately. But probably the most interesting thing about this was that was this so-called extend-on solution. So it turns out that in many quantum cascade lasers, you get this nice linear chirping. And this mean field theory actually gives rise to a simplified version where you have this so-called phase potential. So your wave is actually governed by this very simple differential equation. It's actually, if you look closely, it's basically the Schrödinger equation. So you have this term from the dispersion, which is like a momentum, but you also have this other term which involves a nonlinear phase potential, which you can think of as being like a regular potential, but proportional to the phase of the electric field. And this might be a little too technical for some of this work, but if you do nonlinear optics, one equation that pops up again and again is this nonlinear intensity potential. This is called the nonlinear Schrödinger equation. So this is, again, very similar to the regular Schrödinger equation in that it involves a momentum term and a potential term. But in the usual version, you have this intensity potential. This is actually first written down by Charles Townes, who made the first laser actually in the 60s. The solutions to this are well known. They're called solitons. These Seach solutions. You know, nonlinear equations are very hard to solve in general, but this is one very famous, if not the most famous, optical nonlinear equation that can be solved. And it's a Seach. And it turns out this phase potential one also actually has an analytical solution, which we call an extend-on. So this is turns out to be a wave that has constant intensity and linear late chirp frequency, which is more or less what you see in experiment. Not exactly, but it's the simplified version of what you see in experiment. So it's kind of, this is helpful in that we now actually have the single equation that can kind of describe a wide swath of solutions. And you can actually write down analytical solutions for these equations. I won't go too much into this, but basically you can think of these FM lasers as basically being rapidly self-swept, self-FM. So you have this laser, which is sweeping across the center of its gain medium, and it's producing actually a relatively flat spectrum, which is nice for applications. You want a flat spectrum for applications, right? You want most of your lines. I mean, for an ideal, this is actually much closer to an ideal cone than a Seach, in the sense that over the bandwidth that you have, all the lines are close and very close in intensity to each other. And that's because a nice linear sweeping will always give you a very flat spectrum. And so actually, if you want to go back to this chart that I mentioned earlier, you know, I mentioned passive mode locking where the laser is modulating its own amplitude. You can actually think of these FM combs as being a laser whose phase is modulating itself. So they really fall into this fourth quadrant of phase modulated lasers. And so this is actually fairly powerful. This concept and the reason for that actually comes down to the bandwidth limits. So if you're wondering like how broadband can these potentially be, well, it turns out that actually they can be quite broadband. It depends on the gain medium. So in terms of the other types of mode lockings and cone formation, it's long been known that passive mode locking actually has a better bandwidth than active mode locking, essentially because passive mode locking allows you to modulate as quickly as your gain bandwidth can support. And then the question is, what about these frequency modulated cones? This is probably a little too technical for this talk, and this is one of our recent results. So I'll kind of go through this part fast. But basically, what we showed is actually that these extended solutions, they're also affected by the gain bandwidth, and the gain bandwidth. Because basically what happens is as you sweep too far across the center of your gain spectrum, your amplitude kind of falls off. And it turns out your extender can absorb some of that. So basically, if your amplitude is not, you can have some amplitude non-uniformity, and the extender is fine with it. It will change its shape a little bit. It'll change its chirp a little bit, but it won't actually break down. But if you try to make something that has too broad a bandwidth, well, what happens is actually the extender starts to break down. And so this breakdown is essentially caused by excessive amplitude fluctuations, and these excessive amplitude fluctuations essentially cause it to destabilize. And so what you get is this chaotic spectrum instead. You don't have a nice stable comb anymore. So you get multi-mobilizing instead, which gives you a broadband spectrum, but not necessarily a nice uniform comb. And so actually we did some numerical stability analysis recently, and we showed that actually these extendons can absorb, at least for fast gain media, they can absorb amplitude fluctuations that are proportional to the bandwidth of the laser. Although there is still some question about the limits on the T1 factor. So this is T1, and for people who aren't deep into block equations, T1 is the lifetime of the upper state or lifetime of the population inversion lifetime for the gain medium, and T2 is the coherence lifetime of the gain medium. So T2 is related to the line width. T1 is related to the population dynamics of the laser. And so it turns out that actually these FM combs really do actually support, at least in theory, a bandwidth that can approach the gain bandwidth of the laser. So there is hope for making combs that are as broadband as the laser itself. And also recently what we showed, which was sort of the main point of that paper, was that you can also really shape the gain of these lasers. So one of the major detrimental factors for achieving a broadband comb is really that the gain medium is not flat itself. So if you want to have, it stands to reason that if you want a really flat spectrum and you want a really nice FM comb, you need a really flat gain medium. And if your gain medium, but any gain medium has some curvature, it has some line width associated with it. Even though that line width is, like, even if the gain value is much above threshold, like if you look at this gain spectrum, right, like this value here is above threshold, but it's also very far down from the peak of the gain curve. So what you can do actually is you can flatten these gain media. And one way of flattening them is by adding resonance structures. So actually in this structure, we used resonantly coupled disks. This is in the double metal waveguide platform. So these disks are evanescently coupled to the side of the resonator, and they're spaced periodically along the side of the laser. These lasers also have sharp mirrors on them, so we're actually engineering both the gain and also the dispersion. And with this, we can actually flatten the gain and get a more broadband comb profile. So kind of this is what the general design looks like. Yeah, so that's kind of what these actually, or what the mask actually looks like. So these QCLs, they end up looking quite complicated because they have both DCMs and also discs on them. And of course, you can actually position the discs at different distances from the laser, and so you can get different evanescent, different strengths of coupling, and also different shapes and also different frequencies by changing the diameter of these discs. And so this is a very nice and flexible strategy for really engineering the shape of the gain spectrum. And so actually what we showed is that if you do it just right, with just a little bit of loss, you can actually broaden the gain spectrum by quite a bit, by about 40%. And also, so for example, in this plot, what we're doing is we are actually increasing the depth of the spectral hole. As you can see, actually the spectral hole, we actually get this best, flattest, most broadband spectrum when we add about 4 inverse centimeters of loss, which corresponds to about 10%, maybe 10 to, like, let's say 6 to 10% of the actual peak gain. So not a lot of loss, actually. So a very small amount. And actually, as we vary the current of the laser, we find that the beat node also stays nice and stable, which is one of the ways of indicating whether or not you have a comb. And so it's stable over this very broad range. And so actually, it's a very easy to use comb, but also a very broadband comb. If you go too far with this, then actually you break into this double peak regime, which is one of these regimes that these combs also like to break into, depending on the operating range. And so this result is actually quite comparable to the best tuning results from similar VCSELs. So I didn't get into this when I was talking about QCLs, but one thing you can do is instead of making a comb, you can also make a tunable laser. So a tunable laser actually has a lot of advantages in many applications, especially in terms of sensitivity. But these tunable lasers take quite a lot to make, and they're usually never fully integrated. They usually have some aspect which is mechanical associated with them. And so that is a little bit harder to deal with. But there was some nice work out of Ben Williams' lab a couple of years ago demonstrating a laser which had about 880 gigahertz of tuning bandwidth, actually with a nominally identical, but actually not identical because no wafer is identical. Gain medium, we were able to get about 700 gigahertz of bandwidth out of that, out of a comb. So, of course, the difference is with a comb, you actually have all these lines lasing at once. With a tunable laser, you only have one line at a time. So you would have to, if you wanted to, for example, make an on-chip frequency reference, then you wouldn't be able to do that with a tunable laser. Now, one thing you can do is sometimes, and this is actually kind of one of the things we're working on in this new project, is basically doing the best of both worlds. So, using the frequency metrology, frequency referencing ability of a comb, and using the tuning capabilities of a tunable laser to figure out where the tunable laser line is by beating it with the comb, and then you can tune it around, figure out where it is compared to all your comb lines, and get your do spectroscopy that way. Also, these structures, they extract most of the gain of this laser, about 10 inverse centimeters of gain, which is actually quite a lot. So that's kind of the broad overview of combs, or at least how I see terahertz combs. So there's a lot of different techniques for generating them. I didn't really get into passive mode logging, which is another promising mechanism, but there's still a lot of room for improvement. And of course, whenever I talk about combs, I totally ignore the temperature issue, which is because actually to make very generally speaking, for most of this comb work, we tend to work at very low temperatures because low temperatures are really where you have lots of gain available to you. But of course, as gain media improve and get to be higher temperature over time, of course, the comb temperatures will improve as well. Yeah, so okay, so maybe we'll move on to the last portion, which is kind of on applications for combs. So this is kind of something where I wouldn't consider myself an expert. Actually, I would consider Professor Terahertz to be much more of an expert in this than I am. But this is something we've also done some work on. So this is something I would like to highlight and kind of to give you a good motivation for why these combs are, of course, very interesting. And kind of the big one, I would say, or kind of the big class of techniques, which are really nice, is are these dual comb techniques. So really, in general, I would say combs enable new spectroscopic modalities. Yeah, so this dual comb spectroscopy technique that I mentioned before is kind of the classic example of something you can do with a comb, which I didn't even mention all the critical selling points of it. But basically, just to reintroduce this, you have two combs. They're slightly differently spaced. You beat them together, and by beating them together, I literally mean you just combine them together on a detector. So like beating them together is actually overselling what it is what we're doing. Really, we are not even doing anything but just combining them, right, with a beam splitter, for example. And then you get, by looking at the difference between every pair of lines, then what you get is you get a beat frequency for every pair, and each beat frequency is unique. And that's really the important thing. Each beat frequency is at a different RF frequency. And so what you've done by doing this, by beating these two combs together, is you've made an RF representation of an optical spectrum. So if you have two lasers and they're chip scale, and you have a chip scale detector, this could be a Schottky mixer or an HEB, something like along those lines, then you can, in theory, make this system very, very compact. Like even people have demonstrated chip scale systems or sort of chip scale systems. There's no grading involved. There's no FTIR involved. There's no delay stage involved. It's literally just a bunch of chips that are where you're beating two light sources together. And actually, the biggest thing for these dual comb systems in the blue sky future is actually not even the lasers themselves or the detector themselves. It's getting the light into the sample, right? So you still have to put some of the, if you have a spectroscopic sample you're trying to measure a fingerprint of, then you still have to put your light through it. Okay, so you still need some optics for that. But aside from that, you don't really even need any optics here, which is really compelling. So you can imagine making ultra compact FTIRs on chip for measuring all sorts of things. Maybe even in your smartphone, for example, would be something that would be kind of wonderful if you could do that over a huge frequency range. Maybe that'll happen one day. I don't know. There's another technique that I'll talk about, which is kind of a little bit different. This is not quite terahertz yet, but this is broadband radiometry. So in dual comb spectroscopy has actually been done for a while. So I'll also discuss this radiometry technique, which is a technique for using two combs to measure the spectrum not of a sample, but of another light source. So if you imagine having a light source coming from somewhere far away, this might be from space, this might be from a star, this could be from a satellite, which is far away, right? That you don't have access to, but you want to find all the information about the satellite, and you have some, I don't know, for example, some light reflected from the sun reflecting off of it. Could you measure the spectrum with very high performance using combs? And that's kind of what I'll get into later on. So dual comb spectroscopy is something that's been done for actually it was first done in the low frequency terahertz side by Dan van der Waals' group, I believe, in 2000. But this was at like a few hundred gigahertz. So sometimes it's also called terahertz. But yeah, you can sort of say it was first done in terahertz. When I'm referring to terahertz dual comb spectroscopy, I'm referring to the 1 to 6 terahertz range. And so we did a simple demonstration a few years ago, demonstrating that you could do this, in fact, with these combs. So the actual combs themselves are quite compact. Generally we'd have two combs kind of back to back like this. Actually, the lasers themselves are even hard to see on this little drawing. So most of this is actually the mount. So the mount here is about 1 inch across, or sorry, 2 centimeters across and about 1 centimeter wide. We demonstrated this with a couple different detectors. Actually, one of the challenges with dual comb spectroscopy is you need a very good fast detector, because you need to be able to measure these RF beat notes. And so that's something that is also an area where we need a lot of room for improvement. But we showed that actually you can do a very basic version of dual comb spectroscopy. This was in collaboration with J.R. Gao in TU Delft. We also did this with the Schottky mixer from Virginia Diodes. And actually, Virginia Diodes I'm not sure if there's going to be an electronic portion to this seminar series, but they make a lot of very high frequency instrumentation for the terahertz range. And so the nice thing about these Schottky diodes is that these are actually at room temperature. These HEBs are not. These HEBs are cooled to about the liquid helium temperature. So we demonstrated that you can do this. We didn't necessarily demonstrate that you could do a good version of this. Our collaborators at Princeton and now also at Wrocław did much better versions, kind of using our lasers. So kind of one of the nice things is that you can do multi-component gas spectroscopy. So they showed that you can you can basically do real-time spectral measurements. So that's what this is showing. This is showing a spectrum analyzer as you put a sample in and take it out. So you could see all the heights of the lines change as you do this. And this is all measured on an RF spectrometer. So you don't actually, this is all in real time. There's no scanning involved. That's one of the nice advantages of these dual comb systems is really their speed. So because the effective speed of the system is determined by the difference of the repetition rates, which can be very large because these are chip scale lasers. So their repetition rate is about 10 gigahertz typically, which means you can easily get separations of maybe 10 megahertz. And so that means that you could do spectroscopy at 10 megahertz. So in other words, getting all the lines of your spectroscopic system at rates of 10 megahertz, at least if you have the signal to noise ratio for it. At Princeton, they showed a few years ago that you could do very nice terahertz hyperspectral imaging using these QCL combs. So this is actually a pill that is, well, if you just look at a visible photo, it looks like a regular pill that has a bunch of powder inside of it. But actually, if you do this, look at this in the terahertz, and you do some analysis on the results, you get an image at every frequency in your dual comb system. We did in this case that we didn't even have that many lines that were actually in this system, but there was enough to be able to distinguish the different components of this pill. So this pill actually had several sugars inside of it, and so if you combine the images together, you can get fairly clear representation of the different components of the pill, really from just a few lines, actually. Of course, if you wanted to detect, so this is, in some sense, this is where you already kind of have an idea of what it is that you're looking for. If you're really trying to detect a purely unknown sample and a large colored space, you would need many lines, not just spanning probably the terahertz, but also spanning multiple frequency bands. So, of course, the really wonderful thing would be if one day somebody could make something that was even broader bandwidth than the terahertz, but maybe covering the terahertz and the infrared and near infrared, all on one device. That would be quite amazing, and you could do a lot of things with that. You can also do multi-species detection. So because you can detect concentration so quickly and also individual frequencies so quickly, you can really do like real-time analysis of gas mixing. So they showed that as you mix NH3 and NO2 and N2O4 into a gas cell, you can see all the lines change their profiles really in real time. And again, there aren't even that many lines here, maybe a dozen or so. But you can see that all the lines are actually behaving fairly differently from each other when each of these gases are introduced. So one of the really nice things about, you might be wondering, like, how does this actually compare to other techniques like Fourier transform spectroscopy in terms of performance? Well, actually, it turns out to be quite favorable if you have the comb for it, right? So Fourier transform spectrometers, what's nice about Fourier transform spectrometers is that they work very well for incoherent sources. So you can measure incoherent sources using FTIRs. But of course, these incoherent sources these FTIRs have limitations, and one of the limitations is speed. So you have this, to get the best sensitivity, you need to scan your mirror You don't want to be splitting your beam up amongst different channels. And so that's actually is going to limit the speed at which you can acquire a spectrum. Of course, if you're also using an incoherent source, you generally don't have a lot of brightness available to you. The nice thing about an incoherent black body source like a glow bar is that, of course, that it has oodles of bandwidth, so huge amounts of bandwidth available to you. This gives you the ability to measure over a broad frequency range. But in terms of performance, actually, these combs turn out to be, in some sense, equivalent to FTIR. So they can give you exactly the same sensitivity if you have the same power laser power source, or same brightness source, same bandwidth source. But of course, in general, combs actually have much greater brightness over their frequency span. And also, these dual comb systems are much faster. So you can quite easily with these dual comb systems get megahertz frequency resolution, microsecond sort of time resolution. Which if you want to make an FTIR that did the same thing, you would basically need an FTIR whose size is 300 meters long and whose mirrors are basically moving at the speed of light. So you can actually make systems that are much faster and actually much higher performance than FTIR, at least in the sense of speed and resolution. Now, of course, the trade-off, generally speaking, at least as far as current combs are considered, is bandwidth, right? So if you have almost nothing compares to a black body source in terms of bandwidth. I mean, it's almost embarrassing in some sense that there's been lots and lots of wonderful work on lasers over the years, but still kind of, if you ask the question, well, what's the broadest bandwidth source you can make that emits the most frequencies all at once? It's just a thermal emitter. The world's oldest light source, older than the light bulb, because the difference between a glow bar and a light bulb is that a light bulb has a case, and a glow bar doesn't even have a case on it. So it would be kind of what we would really love to be able to do is replace these thermal sources with actual laser sources, and maybe one day that will be the case. So in terms of performance, these dual comb systems are actually quite nice. Lastly, I want to talk about kind of this newer thing we've been doing, which is high resolution radiometry. And this is very much like heterodyne spectroscopy, where in heterodyne spectroscopy, what you're doing is you are beating a single frequency with a remote signal, and you're trying to measure the spectrum of this remote signal. So whereas in dual comb spectroscopy, you're basically measuring one comb with another comb. In radiometry, you're trying to measure something else. So something that's not a comb necessarily, something that maybe isn't even narrowband. It could be something that's very broadband. It could be anything, actually. It could be light from a star, could be light from the sun. Could be something you're trying to image. An incoherent source, coherent source, doesn't matter. And the ultimate frequency resolution in this case is actually quite good in heterodyne spectroscopy. It's the reason it's used actually for radio waves and also for terahertz. And it's basically 1 over the measurement time. And what you measure is by beating your local oscillator with your signal, you measure a down-converted copy of your signal. And this down-converted copy is very high resolution. And this is ideal for long wavelength because you can make very high resolution spectrometer or radiometers with very small devices. So actually, heterodyne spectroscopy is not ideal in terms of sensitivity, but where it's ideal is in achieving a small or high resolution, but in a small form factor. It turns out that actually, as you go to long wavelengths, if you want to, for example, make a grading spectrometer that has high resolution, your grading spectrometer would need to grow to a ridiculous level, right? So if you wanted to have a resolving power of the resolving power that you can achieve, which is basically the ratio of like your finest frequency bin to your frequency, is basically proportional to your wavelength times the size of your structure divided by your wavelength. So if you wanted to achieve a resolving power of, let's say, 50,000, then you would need a structure that is 50,000 times larger than your wavelength, which for millimeter waves, right, is 50 meters, right? So as you go into longer and longer wavelengths, you would need increasingly gigantic gratings in order to achieve high resolution. So while these heterodyne spectrometers are very fast and high resolution and sensitive, they have very limited bandwidth. So if you down convert your signal, your span is basically only over the span over which you have detector bandwidth. So your detector can only see a certain amount of bandwidth. It's typically a few gigahertz. And so if you want to see beyond that, you would need to tune your laser around. And actually, that's something that's been demonstrated by Scott Didham's lab. You can tune your laser around, and if you know where your laser is at all times, then you can measure by beating your remote light source with your tunable laser, and then you can actually measure what the spectrum actually looks like. And of course, it'd be really nice if you could do this in the terahertz as well, because there are these really wonderful terahertz QCLs. And if you can do what I mentioned earlier and beat a terahertz QCL with a comb, then you could potentially get very high sensitivity and high resolution radiometers. But kind of what we were thinking a couple of years ago was, is it possible to do heterodyne spectroscopy with a comb directly? So something like dual comb spectroscopy, but using a comb as an LO. So beating your comb with a remote signal. And well, you can think about doing it, but you run into problems right away. And the big problem is that if you beat a comb with the signal, if it's a broadband signal, and you have all these comb lines, yeah, you get around this detector bandwidth issue. But you don't actually know which comb line you've beaten with. So you basically fold all of this whole frequency span down into this very narrow bandwidth range. So a comb by itself is not enough to unravel this beat frequency. And so we were thinking of if there's a way of doing that. And it turns out there's a very nice way of using a second comb. So all of these, everything comes down to the dual comb technique when it comes to frequency comb spectroscopies for the most part. The general reason for that is that almost any interferometer type system can be replaced with combs. There has been some work on this area, especially these dual comb product methods, been demonstrated by a number of groups, and then also these vernier methods. And actually, the Hall group did both of these two things separately, but not all at once. So these dual comb product methods, they give you a very broadband incoherent spectrum, but they give you very low resolution. Whereas these vernier methods give you very high resolution, but they only work for coherent spectra. And of course, what you're wondering is if it's possible to achieve heterodyne resolution while also measuring broad features. And so kind of the first thing we came up with was something like SWIFTs. So SWIFTs is actually an example of demultiplexing the multiple beat notes of a comb using an FTIR. So all these beat notes are added on top of each other. They're all at the same frequency. So how do you separate them out? Well, one way is, can you use an interferometer? And it turns out the answer is no. You can't by itself. You can't use an interferometer by itself in order to do this measurement, to separate out these different beatings. But you can do something like an interferometer. So if you have two combs, or if you have one comb and you delay one copy of the comb and you beat that with your signal, and then you do the same thing with the undelayed version of this, and you actually get and so in other words, you have two detectors. It turns out that with these two detectors, that actually is enough information to reconstruct the whole spectrum of your remote light source over the bandwidth of your comb. And I really won't go into the math because it's a little too technical for this. But basically, it involves multiple Fourier transforms and correlations. And we call this the tachyscopic conversion algorithm for reasons I'll talk about in a second. It's correlating your spectrograms and then Fourier transforming a delay. And you can show actually that what you get when you do this is you get, by doing this Fourier transform, you get the product of every comb tooth power plus the local spectrum of your light source. In other words, this mini spectrum. And well, it's essentially it's a correlation-based measurement, so that's why this actually works. But of course, this is using an FTIR. Can we do something with the dual comb version? It turns out the answer is yes, using this mirror between interferometry and dual combs that I mentioned before, which is that almost any interferometer can be replaced with a second comb. A second comb that's differently spaced is essentially equivalent to a constantly moving mirror. So that's why this is very similar to an interferometer. And so you can do a dual comb version of this. So if you take two combs and you beat them with the remote light source, again, you'll have two signals. You record them separately. You correlate the spectrograms, then you Fourier transform in slow time. And then again, you can actually recover the full spectrum doing this. So we actually demonstrated this initially in the microwave, although we have a new project for doing this in the terahertz. So this is maybe not a fully terahertz measurement, but it's a microwave measurement using step recovery diodes. So there's nothing frequency specific here. It's just it was the amount of data that you need to process in order to do this measurement is quite involved. But yeah, this actually does work. So actually around each of these comb lines, you get this very high resolution miniature spectrum. And this high resolution miniature spectrum, actually, if you look, it kind of decays away from each pair of comb lines. Each pair of comb lines is indicated by these little pairs here. There's a lot going on in this plot. So, but yeah, you can see that each of these mini spectra is centered around a single frequency. And so when we take all these things and we basically stitch them back together, we do in fact get the composite spectrum of our radiation source. So again, we get this dual comb beat signal that times the local product of the spectrum. And this is very analogous to Fourier tachography in some sense, which is a technique for computational imaging. In that sense, in that case, what you're doing is you're measuring very wide field images by illuminating at different points in K-space. We had a collaborator who thought this was very similar and that we're sort of doing the same thing in frequency space. And so we decided to kind of call it tachoscopy. Tycho basically means fold in Greek. So all these lines are kind of initially folded on top of each other, and you have to do this. You have to use this algorithm to essentially unfold them. And so we actually showed that this does in fact work. So if you have this very single frequency line and you do this tachoscopy technique using combs to measure it, you can actually reconstruct the spectrum of this line very effectively. So even though we have this very low bandwidth detector, in this case, it's only 20 megahertz of bandwidth, we can actually recover the spectrum of this radiation source over a range that's much greater than that. You can see that a single line was produced. This is on linear scale. On a log scale, it's not quite as nice, but there are some imaging artifacts that you always get, extra noise and so on and so forth. But it's still about 20 dB down. So you still get this relatively high quality spectrum. Of course, you can also do this for octave spanning spectra. We demonstrated that as well. So if you have multiple lines with combs that are octave spanning, then you can actually still reconstruct these spectra. The lines are exactly where you would expect them to be, despite the fact that you're measuring with a much lower bandwidth measurement technique. Here, the resolving power is 150,000, and the frequency is, 2 gigahertz? So if you wanted to do the same thing with a grating spectrometer, you'd be looking at least kilometers. You need a kilometer-sized grating spectrometer in order to do this sort of measurement. So this is something that it would be basically impossible with a grating spectrometer. But with these multi-heterodyne techniques are actually quite possible. We also measured very broadband signals. I don't want to go into this, but there's a lot of calibrations that you need to do in order to get very accurate measurements. So the raw signals actually never look exactly like what I just showed. The raw signals actually end up looking like this. You really need to calibrate both for the changing comb strengths and also the changing teeth strength. And so when you do that calibration, you can actually see that everything kind of agrees nicely with each other. One thing that's interesting is that you actually have a little bit more bandwidth. If you have detectors with more bandwidth in your comb spacing, then you can actually get a little overlap between each line with its neighbor. So you get like basically multiple competing versions of the same spectrum. So that's why, for example, these two lines are on top of each other. But actually, that's one way of verifying that this technique is actually doing what we think it's doing, right? Is that if all these lines where they overlap more or less agree with each other, then actually this calibration and measurement actually is working very well. And then when you stitch everything together, you get this nice spectrum. In this case, it was a Gaussian spectrum. We also do this with a more complicated broadband signal with this Terahertz technique. Again, we showed that you can do this with both for both broadband features, but also features that are narrower than the comb spacing. So that's important. You're not just picking high resolution or broadband coverage. You're picking, you're getting both at the same time. And well, the sensitivity of this technique, you might be wondering, it's never going to be as good as a tuned local oscillator. There's very fundamental reasons for that. But actually, in many cases, sometimes it actually can be close for technical reasons, actually. So for this measurement that we were doing here, basically part of the challenge is that tunable spectrometers have difficulties measuring spectra that are not purely governed by white noise. So like, for example, if you have a frequency which is rapidly sweeping around and you try to measure this with like a tuned local oscillator, your signal is going to be very bad most of the time because sometimes as you're scanning, if you have your signal doing this and kind of moving around randomly and then you're scanning linearly across that, then you'll get these very random fluctuations between each successive scan. And so your SNR is usually going to be quite poor in that case. And so in this case, actually, Terahertz does quite a bit better. For purely incoherent spectra, it's usually not going to be as good, though. That's, yeah, basically enough time. So in conclusion, I think Terahertz quantum cascade lasers talked about a lot of topics relating to them, but in general, they're appealing sources in the terahertz that offer high powers at, well, close to room temperature. Maybe room temperature soon. We'll see. I think there's a lot of nice interest in general, there's a lot of interest in active cavity nonlinear optics enabled by QCLs, especially Terahertz QCLs. The one that I focused on today was mostly this FM comb state, which is interesting for a lot of applications. We think broadband combs based on QCLs are very potentially attractive options for spectroscopy, including both measurement of samples and spectra. I will say I'm looking for a postdoc. We have a new multi-university project in the US. It's a 8PI team. Actually, a lot of this Terahertz and comb spectroscopy work is going to be covered in this new project. So that's something we're pretty excited about. The topic is called PRISM because it's about radiometers. And of course, it's about combs more generally. So if you're interested, please email me. I think you can find my email relatively easily. I'd like to thank all of our collaborators, especially for the people who did the papers I focused on most extensively for this work. So Ethan, our MBE grower, Savvikas Adamain, and previously John Reno, David Burghoff, who did the spectroscopy work, Professor Strachewski, who did a lot of the spectroscopy work, and many others as well. So yes, that's all I have. I hope there's the time for a few more questions, for a few questions at least. So thank you all for your attention. With that, I'll end my talk.
Thank you again, David, for this outstanding lecture. And so yeah, with this, let's open the Q&A session. Everyone is more than welcome to input their questions within the Q&A part of Zoom. In the meantime, maybe Łukasz would like to say a few words.
Well, as always, impressive lecture and a lot of perspective. Maybe the first question I can ask: do you envision that terahertz QCLs will ever operate at room temperature?
I used to be pessimistic. I am now optimistic. There are some tricks that you can play if you are willing to do them. That well, we're interested. I'll put it this way. Up until like maybe last year, I had not too much interest in like trying to like really push for that. But now I actually kind of am. So I'm optimistic. Now, here's the thing. At 4 terahertz, I think the answer is for sure yes. But at 5 terahertz or at 2 terahertz, yeah, that's a little bit harder. I mean, there's certainly there. Well, in addition, so keep in mind that all these record results are in gallium arsenide algas. That's one material system. So people are always coming up with new systems. There's the new one on the block, which is interesting for a lot of reasons, which is 3 nitrides, but with scandium as barrier materials, which are interesting for a lot of reasons, including that they're ferroelectric, but apparently they're also much easier to grow than conventional 3 nitrides. So yeah, they're not quite there yet, but it's possible that they will get there. So one of the reasons that 3 nitrides are so appealing is that they have a very high LO photon energy. So it's the defect between your temperature and your frequency. If it's lower than the photon energy, then you're going to be having trouble maintaining inversion. So in gallium arsenide, that energy is about 36 MeV, but in 3 nitrides, it's about 90 MeV. So so for a long time, people have wanted to make QCLs out of gallium nitride and algan. It's just they've never really worked, and even at 4 Kelvin, and a lot of that just has to do with sheer material growth. So again, I'm not an MBE person, but I am told that these gallium nitride, scandium aluminum nitride are actually you can get better interfaces with them. So and they also have similar LO photon energy. So who knows? Maybe in a few years we'll see.
Okay, great. I think we have one question in the Q&A box, and I'll let you read and answer the question from the audience.
Yeah, so the question is, why do the spectra not look so nice? So basically, yeah, part of it is that they can look very nice. It depends on the system you're using to measure them, I guess. So there's the group. Well, there's one group that has demonstrated that also Jerome Feist's group. They also work on these combs. I didn't show too many other results. I showed the very broadband result, but they use a vacuum FTIR, and so they always have very, very nice spectra. In our case, we are generally relying on purging. So our system is going through our combs are generally going through a pretty large amount of atmosphere, and so we have a lot of spectral modulation on top of it. So those combs are never quite so nice looking. If you do some work to, yeah, I mean, like, yeah, if you do more work to improve the system, then they suddenly look a lot nicer. I'll say that. Yeah.
Yeah, but I'd like to add one more comment that multimode emission seems to favor relatively flat operation, whereas when you jump into
emission is often very nice. Yeah, of course, if you can crack that nut of doing dual cone spectroscopy with a multimode laser, which is not crazy to think about, right? Like that's something that would be like in theory you can do it, right? Like if you have if you actually know, no, actually, let's see, can you do that? I mean, you'd have to do some serious math on the back end, but I mean, like if you could figure out a way of doing coherent spectroscopy or frequency referencing with something which is actually, you know, fairly incoherent, then you may actually be able to do all this stuff with a multi-mode laser, in which case you don't even need to comb, right? If you have the bandwidth available to you, that's in some ways better. So yeah, I mean,
yeah. So let's hope one day we'll. Yeah.
Mode of opportunity, I guess.
Okay, we have one more question from the audience.
With triple or N combs. So the question, could you clarify triple meaning like skipping every other line, or do you mean like harmonic combs?
Yeah.
Okay, yes. Well, in terms of, I mean, not generally. You know, one challenge I would say, I mean, so actually these kinds of combs do exist. They're called harmonic state combs, and I didn't really get into them. And actually, it's another mode of operation that sometimes these QCL combs fall into. And basically, it's a mode of operation where the laser decides to skip every nth line. And you can do this through a number of techniques. Sometimes it just happens spontaneously. You can also add defects to a cavity in order to do this. Actually, in my first Terahertz QCL combs, they had this behavior as well. I don't know if you necessarily want to do that because the repetition rate is also quite high already for a lot of these systems. So the repetition rate is already, you know, on the order of 10 gigahertz, let's say. So, you know, if you're talking about skipping every other line, every third line, fourth line, you're looking at very high repetition rates. And in that case, it's hard to do any applications with those states, right? Like you don't have that many lines available. Your lines are all spaced by a huge amount. If you wanted to cover that space in between, you'd have to tune everything around, which maybe you could do that, but or you have to have a very fast detector, like a detector with, you know, 20, 30 gigahertz of bandwidth, which is already a challenge. So generally speaking, in terms of like harmonic combs, I am not so optimistic about applications for them. But you know, maybe there's some where like if you wanted to get more power per tooth, that might be an application. You know, like at least in my opinion, like you kind of want to go one of two directions. You either want to go all of your power on one line, right? That's a single line laser, or you're willing to split your power, and in that case, you want to have your power split amongst a bunch of lines. But you don't want to have too few of those either. So I don't know. It's a matter of opinion, I guess.
Okay, so we have a rare situation in which we have a question from the future lecturer in this series. So Professor Wojciech Knap would like to ask a question.
Yeah. So so MBE technology. So
he's actually here, so let him also ask the question.
Oh, sure.
Yeah. Can you hear me?
Yes.
Yeah, I can hear you.
Can you hear? Yeah. Okay. Now the question is: you started your lecture telling that MBE technology for quantum cascade laser is the only one you can use, but it's so not reproducible. Even inside one wafer, you have a spread of the parameters. So if it is so no reproducible, can one make any reproducible comp devices out of it?
So inside a wafer, it's actually very reproducible. I mean, there's always a little bit of a gradient inside a wafer, but So like a lot of the devices I showed, like for example, involving the chart mirrors, involving the gain shaping structures, those are actually relied on measurements from other devices that we fabbed before fabbing these devices. And then we took the parameters from those from the previous fab and then applied it to make our design. So generally speaking, like it depends on how many, I guess it depends on how many devices you want to make, right? You can make a lot of devices with a 4-inch wafer. You can make, thousands in theory, but it takes some effort to replicate that wafer. And when you replicate it, it doesn't quite replicate perfectly. So like many people in this area have had this experience where they see a design in literature and they try to grow it. And they grow it like 3 or 4 times. Then eventually they get something that is more or less close enough, and they decide, okay, yeah, we'll use that. So you can get something approximating it, often with multiple attempts. But yeah, they're a little bit. Their uniqueness is definitely an issue. If you are trying to have many, if you're trying to have like fabricate millions of these things, then that could potentially be a problem. At the level of course, where people are currently doing these things, you can get thousands of devices from a wafer, so it's not really a problem. But
yeah, okay, it's clear. Thank you.
And we got one more question through the Q&A.
Yeah, so what is the stability, repeatability of measurements? They are quite good. So actually, generally speaking, for most quantum cascade lasers, I mean, there hasn't been a huge, there hasn't been a huge amount of what's the word? Lifetime analysis. But basically there has been some, and generally what happens with these lasers is there's like a settling in period. So once you've biased it in continuous wave mode for a certain amount of time, it kind of, the power, the spectrum, everything kind of stabilizes out at some plateau, and it stays there for many hours. It's been measured, I think, at least at like 15,000, 20,000 before there's any change. And then sometimes you start seeing like changes after that also. So I think that's a pretty typical bathtub type shape that's associated with the power in the spectrum.
I mean, we can also comment on the stability of dual comp measurements in terms of relative amplitude fluctuations, which from empirically is on the order of 10 to the -2. So percentage level of precision per millisecond, let's say. Those are the numbers in terms of amplitude stability. So do we have any other questions?
Okay, it seems we've run out of them. So with this, I'd like to again thank David for this amazing lecture and for the Q&A session. And next week we will have Tom Seifert, who will tell us about ultra broadband spintronic terahertz emitters and detectors. So thank you all for coming in today, and see you all next week.
All right, thank you.
Thank you.
Thank you, Dave. Bye. Thank you, everyone.